Good morning, everyone. Thanks for coming so early for my talk. So, myself Bhavna, as Santosh introduced, and I'm coming from Carnegie Mellon University, and today I will be talking about semi-supervised learning in realistic settings. I will soon tell you what do I mean by realistic. This is work done under supervision of my advisors, Professor William Cohen and Professor Jamie Callan. Let's start with the outline of this talk. So first I will tell you some background about my research and give an overview. Next we will look at 3 semi-supervised learning scenarios, the presence of unanticipated classes, class hierarchy and multi-view data. I will then go in depth of first 2 approaches. Later we will see some applications of these techniques and some future directions and other research projects that I have worked on. So let's start. So who am I? I am coming from this Read the Web group at CMU, led by Professor Tom Mitchell and Professor William Cohen. And all the lovely PhD students in this photograph are working on some cool machine learning problems in the area of information extraction to populate knowledge bases. This is a pic taken at 5th birthday of our knowledge base NELL. So let me tell you what we do. So we build knowledge bases. If some of you are not familiar with what knowledge base is, it has these ontology of classes where we know that there is a concept called city, and this is of type location. So we have been given some hierarchy of these classes, and there are facts that it's trying to learn of this type. Pittsburgh is of type city, USA is of type country, and so on. There is some more information in the knowledge base in terms of relations, attribute values and text descriptions. And such kind of knowledge bases are very useful in tasks like question answering, co-reference resolution, and these days in web search. So how we do it in CMU, this is a very simple diagram that how I look at it, how I look at the system. So we call it never ending language learning. What it's trying to do is it has some ontology of concepts that was human created, and someone gave some seed facts to bootstrap the learning. There are many unlabeled data sets that are extracted from web scale corpora like ClueWeb. And in terms of unlabeled data, we have different kinds of features like text patterns, HTML tables, and so on. So these semi-supervised learning algorithms are trying to leverage this different kind of data to produce more facts that can be added to the knowledge base. And this process is iterated over and over again. That's why we call it never-ending language learning. So the important part for this talk is there are many such semi-supervised learning methods, and I will be talking about some of these that we apply. The research, the PhD research that I am working on was motivated by the application in NELL knowledge base, but the techniques that I will present today are generic and they can be applied for any classification or clustering task. So let's look at what do I mean by semi-supervised learning. So on one side, we have these supervised learning techniques where we know lots of labeled data points, say blue and red. We have been given this data, and the task is to find out a classification boundary that can distinguish between these 2 classes. Okay, on the other end of spectrum, we have unsupervised learning techniques, also called clustering techniques, that given a large number of unlabeled data points, black circles here, they try to find out some groupings in this data. So for example, if we say that find 2 clusters, it will group them into 2 such clusters. I am particularly interested in something in between these 2. So we know large number of data points, unlabeled data points, which are black circles, but someone manually annotated for us these small number of seed examples, or we got them for an independent data source, and the task is to label rest of the data points. Okay. So this can be done either as semi-supervised clustering or semi-supervised classification. Here I am showing you a pictorial representation of how clustering works. So we first initialize the seed data points with some mean of the labeled data points, and then we propagate these labels using an iterative approach. Finally, we have something like this. This is called semi-supervised learning. Okay, so now let us see what 3 realistic settings that I want to introduce. The first one is novel. It's incorporating the fact that some algorithm might not know about all classes present in the data. So it might start with some categories, and unlabeled data might have some unanticipated categories. The second scenario is where the classes are arranged in a hierarchy, or they have constraints like class A is subset of class B, or class A is disjoint from class C, and we would like to do better learning in this case. The third setting is where each data point can be represented by multiple views. And if this is very abstract, I am going to give you examples for each of them. So the first setting is my favorite one. It's called SSL with unanticipated classes. So say your system knows about these 4 categories: mammals, reptiles, fruits and vegetables, and you have been given some labeled data for each of these categories. Okay, small number of seed examples. Now we go to large amount of unlabeled data. So this was extracted from a large web scale corpus, and there are many interesting entities here. If you want to classify them into one of these 4, some entities might get classified correctly, but you can see that there are many interesting birds and monuments here, but we don't know about these categories. And this is what I am referring to as unanticipated classes. If you look at them closely, they nicely cluster into groups of some consistent categories, and the research question we want to ask is, can we simultaneously learn classifiers for the known categories as well as discover these unanticipated ones in a single learning framework? Okay, so this is the research question. Second scenario that I want to talk about is, say these same 4 classes are now arranged in an ontology, and we have subset and disjointness constraint. So here I am saying that if some data point is categorized as mammal, it should also be categorized as animal, and any data point can either be classified as mammal or reptile, not at the same time. So with this kind of hierarchy, now we can learn classifiers for each node in this ontology. So instead of doing that only for the leaf nodes, we also learn what do we mean by animal and food. Okay, so this is the second case. The third scenario is when we have multiple data views. So say there are these 3 cat data points, and we have their images as well as text around these images. Then instead of concatenating these 2 feature vectors, we can learn an image classifier, an independent text classifier, and combine their scores using some intelligent multiview method. Another popular example of where people do multiview learning is web document categorization. So say we have the document text, we also have links between the documents that give us some anchor text, and the third view can be user generated tags. If you can model them effectively in 3 different learning models, then you can join them in a multi-view learning setting. So these are the 3 scenarios that my thesis focuses on, and I have some publications either in submission or already published. And we have also worked on combinations of these. So I have worked on hierarchical exploratory learning and multi-view hierarchical learning. Today I will be talking about the first 2 parts, exploratory learning and hierarchical semi-supervised learning. Please let me know if you have any questions till now.
The multi-view, is that the co-training idea?
So good question. So co-training can be one approach of multi-view learning, but we are proposing in my work we are proposing another method which is supposed to work better than co-training. But yeah, co-training is one method. Any other questions? Okay, perfect. So let us move on to the first part, which is exploratory learning. And we are trying to model unanticipated classes here. So I showed you this cute little demo where we want to learn these unanticipated classes. But you might wonder that now that we know there are birds and monuments in the data, why not just add those two classes in the set of categories? And we already know the sample data points for them, and the problem is solved. But I would say that no, the problem is not solved, because now you go again to the web scale corpus and there are beverages and cities which you haven't modeled. Okay, so it's not about finding out few classes in the unlabeled data. It is more about if you are going to some unlabeled data set in which you don't know all the classes, can your semi-supervised learning be robust to these unknown ones and learn the known classes in still in effective way? You are not gathering some garbage from the unlabeled data. So keeping the known classes pure as well as discovering the new ones is the focus of our work. Okay. So let us first see what semi-supervised learning techniques are doing, what is the limitation that they have, and then we will propose our own method. So let us start with problem definition of semi-supervised learning, basics. So here as input we have large set of data points x1 to xn, and we have been given some set of classes c1 to ck. There are some small number of seed examples labeled for all of these classes, and the output that we are expecting is for each data point xi we generate some label that is coming from c1 to ck. To solve this problem, there have been like many approaches proposed, but one of the very widely used one is classification EM, where EM refers to expectation maximization. Here is how it works. So for each class Cj, we have some model parameters theta j. For the first iteration, we are initializing them with the help of seed data that is given as input. Later, we are iterating till convergence 2 steps. In the each step, we are predicting labels for unlabeled data points. So here we are computing this posterior of class Cj given data point xi. This posterior is computed for all data points, and that label is selected, which gives maximum posterior probability. In the m step, we recompute the model parameters. So here the parameters theta j for class j are computed for next iteration t plus 1. Based on what parameter values give maximum likelihood of seeing this data and labels predicted in this iteration. Okay. This process is iterated till we converge on the log data likelihood. So this is the classification EM algorithm. The problem that we saw in this case is semantic drift. So here the unlabeled data points might not belong to any of the existing classes. And if we don't take care of this fact in systematic way, then we are going to end up in semantic drift. To show this in a toy example, we saw that these 4 data points are correctly classified, but we might also classify some of the birds in one of the animal classes. And this is what I mean by semantic drift. That was a toy example created by me, but what happens in a real world data set? So say we have 20 newsgroup data set. Here we know that there are 20 categories, but we fooled the semi-supervised EM algorithm by saying that there are only 6. So the rest of the 14 categories are unknown to the algorithm. Let's see what it does. What I am plotting here is a confusion matrix after iteration 1 and iteration 15 of EM. The ideal matrix should look like this. It should be all blue and red diagonal, and 6 blocks in the red diagonal because it knows about only 6 classes. What is happening is over the iterations, it is confusing the predicted classes which are on x-axis with actual classes which are on y-axis. There are only 6 columns because it can predict only 6 classes. Okay, so this is the semantic drift in real world. What I am going to propose is an exploratory EM algorithm that can reduce this semantic drift. So if you look at the confusion matrices, now it has discovered some new categories from unlabeled data, and thereby kept the seed classes more purer than the semi-supervised EM. Okay, so we want to achieve this. To achieve this, we modify the problem definition of semi-supervised learning like this. So now the algorithm can discover classes from data. So instead of k classes, now it can discover m new classes, and the data points can belong to any one of these k plus m classes. To keep this problem non-trivial, we need to add this constraint that k plus m should be orders of magnitude less than n. Otherwise, you might end up creating a new class for each unlabeled data point and get maximum likelihood. We don't want that. Yes?
Okay, what are your data points? Are they features considered or what?
Yeah. Good that you asked. So the data point xi can mean either a document that you want to classify or an image that you want to categorize, or anything that can be represented by a feature vector.
And I mean, what are the actual features?
Sorry?
I mean, for the experiments, what exactly did you use?
Oh, so we applied it for different kinds of data. One was semi-structured data, where the features were co-occurrences in table columns, HTML table columns. Other was 20 news group, which is a document classification data set. But yeah, it doesn't matter. Yeah. Thank you. So now let me show you how we extend the classification EM algorithm that I showed you earlier for this particular modified problem definition. So we again follow the same iterative EM model. The change is shown in green. So what is happening now is that for each data point xi, when we compute this posterior, instead of directly assigning it to the maximum probable class, we are first checking how that posterior is, like is it satisfying some new class creation criteria. And for now, assume that we have an oracle that tells us new class needs to be created for this data point. I will tell you what that oracle is later. So say we have this criteria, then we can create a new class for that data point xi for which this criteria is satisfied. If that class, if it creates a new class, then parameters for that class are initialized with this data point for which it is created, and this is done sequentially. So for ith data point, if k plus 1 class is created, then for I plus 1 data point, this class is one of the available classes. It can join it. Okay. In the m step, the difference is now the number of classes might have increased because of the addition of classes. So it will relearn the parameters for all available classes. Finally, to avoid creating too many classes, we do model selection at the end of each EM iteration. Here we are checking whether the model selection criteria is satisfied. So we are comparing two models, one with addition of extra classes and one with same number of classes as previous iteration. Whichever model gives best penalized log likelihood score, that model wins and goes to the next iteration. And the iterations are continued till data likelihood as well as number of classes are converged. Okay, so this is the procedure. It's a simple change in EM algorithm. Now let's see how it will work for our running example. So the first three data points are sequentially going to one of the existing classes. Now the bird comes and it creates its own class. The next two data points join the existing cluster. So for this bird, the new class 1 was there. Then comes the monument and creates its own class, and rest of the data points join. So this is how ideally exploratory EM should work. So in this particular solution, there are three unknowns here. Which model one should use? I haven't told you about the new class creation criteria and what do I mean by model selection. I will tell you each of this in next few slides. Yes?
You don't have any regularization on the number of models. I think what maximizes that likelihood would be one parameter, for instance.
So you are saying not creating, what we do for not creating too many classes?
Yes.
That is what is model selection about. I will come to that point. Okay, so the first question is how we detect how to create new class. So for each data point xi and current number of classes k, we are defining a posterior which is already computed for semi-supervised EM, which is probability of class given a data point, and we are comparing it with uniform distribution, which is 1 over k for current k. Okay. The first criteria that we have proposed is Jensen-Shannon divergence, which is computing the divergence between posterior and this uniform probability. If this divergence is less than 1 by k, then we create a new class. Simple math. The next criteria is even simpler. So we compute a maximum and minimum probability in that posterior, take a ratio. If that ratio is less than some value, say 2, then create a new class. And you can apply many such heuristic based criteria here, like you can say the maximum and next to maximum probability, how much is the skew. Or one can train their own classifier based on these as feature values and with some validation data. But we checked these simple criteria and they worked. The next question was, as you said, model selection. So how do we make sure that we are not creating too many classes? For that, our objective function is penalize log data likelihood, which is computing log likelihood minus the model penalty. So if we create many classes, it's penalized. And this is done to optimize number of classes as well as parameters for those classes. This particular objective function is computed using model selection criteria. And here you can use any training error based model selection criteria. We tried the popular ones like AIC, BIC and extended AIC. For our data sets, extended AIC criteria worked best because we have large number of features compared to number of data points. And this is a simple criteria proposed in 2004. What it has is log data likelihood term and model complexity term. So one of the models which has best score on this AIC will be picked. Okay. The next question was which model one should use, and this will depend on your task and your data. So for image data you might want to try different models, but we tried these three, which the first one is classification, semi-supervised naive Bayes, and next two are clustering models. So this procedure can be done either for classification or clustering. Let me show you how we did it. So for the semi-supervised naive Bayes, it's assuming multinomial model and picking that label for each data point xi which gives maximum posterior. We follow the same process, just that we check first whether it satisfies new class creation, and if it does, then the multinomials for that particular new class are initialized with this data point xi and we move forward. For seeded k-means, now this is a clustering algorithm, there is no posterior probability. But what we can do, we can normalize both the centroid and data point and take their dot product as similarity measure. The seeded k-means version will choose for each data point xi the closest cluster. It's called seeded because it can make use of the supervision that is provided to it. The exploratory k-means checks this dot product vector for new class creation criteria. If that is the case, then it creates a new cluster and initializes its centroid with xi. Otherwise, it is following the same procedure. So from this solution, I told you how you can choose different models. Any model that fits EM framework, which is probabilistic, can be applied here. For the new class creation, we propose min-max and Jensen-Shannon, but you can try your own criteria. And for model selection, you can use any training error based model selection. Yes?
So just to kind of make sure I understand. When you're choosing to create a new class, it's like you're looking at how it fits with all of the other classes, and if that's close to uniform. So does that mean when you're using the k-best one, k-means one, that if basically you have this point and it's roughly equally far away from the centroids of all of the other clusters, then you create a new cluster?
Yeah, so it might look counterintuitive for two-dimensional case, but it works very well for high-dimensional data sets. Because if you are in high dimension and if this point is coming from some other category, then it looks equidistant from these classes. That's what we saw.
I see. But if there's like a case where you have this far-flung cluster that has one of the cluster that's a lot closer to it than the other ones, then it won't discover that.
That might happen. That's why these criteria might not work for all data sets. But yeah, you can pick the one which works best for the task. Sorry.
Quick question as well. So if the model selection criterion fails, you revert back to the previous model.
Mm-hmm.
So how do you prevent just relearning the bad model over and over again?
Oh, so if the parameters are not changing over iterations, then it's converged to local optima for penalized log likelihood.
But it looks here, if the E step doesn't generate a model that passes the selection criteria, you just repeat the E step again with the same inputs.
Okay, yeah, good question. So yeah, so what is happening is we are not just reverting back to the previous model, but we are reverting back to the previous set of categories. So during this iteration, we have relearned the previous set of categories with new assignments, assuming these categories are fixed. So it's not moving back to the same assignments as previous iteration. I should have made that clear, yeah, good point.
And it looks like your algorithm is order dependent, or is it order dependent?
Yes, it is order dependent. And that's why it is also not parallelizable in the E step, if you look at it.
So that seems like an undesirable property that the order of the examples will affect the learning.
Yeah, so we have thought about some ways of overcoming that. So for example, you can shard the data in the map-reduce kind of framework and learn these exploratory models per shard. If the sharding is based on similarity of data points, then hopefully there are not too many clusters which are overlapping, but you can do a post-processing step and merge them. So something like that can be done, but it is order dependent, yes. Yeah.
It seems to me that there would be cases, or data sets rather, where the performance of the algorithm really is dependent on the order of presentation of the data points.
Mm-hmm.
Did you look at that issue at all?
So not in this particular paper, but we have done that for our other paper, which is web sets. So there, what we observed was that if you rank the data points in some desirable order, say for each data point you have some co-occurrence features. If you rank them by their co-occurrences, then you get the most popular points first, and they create new clusters and rest of the points join them. And that helped a lot in the web sets, in that project. But we haven't really explored it here. Yes?
So one thing that relates to this ordering issue and also the model selection issue is it seems like if you have an oracle for that new class creation,
Mm-hmm.
you could just use it to say if this thing doesn't fit any of the existing K classes, the supervised classes, I'm just going to keep it unlabeled instead of trying to create a new class seeded by the first thing you see in that order. And keep it unlabeled. At the end, you end up with K plus 1 things. The K plus first is unlabeled.
Mm-hmm.
Separate that problem, treat it as an unsupervised learning problem. Is that something you think might work, or you consider?
So we haven't considered exactly same baseline, but we have considered other baseline, which is referred in the paper, which is, say if you learn how many clusters are there, and you learn best M clusters that can be added to semi-supervised k-means, given the test data, then like is it better than exploratory EM? And our experiments show that no, this is better than that, and this is also feasible. So
Whether it's
maybe.
better or not depend on how successful the learning was. I mean, if you have a strong notion of how many additional classes are available, then that's going to work better, either from a prior or from the learning process. Is that clear?
But I'm saying that if you use test data and find best number of extra classes, Still this method gave some improvement because we are not just creating a new cluster, we are seeding it with a data point that is not belonging to these. So even that seeding is helping in some way. That is
that
what.
was part of my point. You're seeding it, the first thing that you see, if you collected all unlabeled things, you could seed them with like means of, you could do standard clustering that will not look at, that will be order independent and things like that,
Yes.
possibly.
Yes, we can explore that. Good suggestion. Thank you. Yeah.
When you revert and drop one of the new classes, I guess everything that was in that new class, you unlabel it and put it back in the pool of unknown things?
No, so that's what I answered in his question. So we are not reverting back to the assignments in iteration t-1. So in each iteration, we have two models that are being evaluated. One with previous number of classes. Consider it as semi-supervised learning task with previous classes. You are assigning it to the maximum probable class. And the second model that is being learned is adding new classes. And at the end, we are comparing these two. So it's not same as previous iteration. Every data point is labeled, yeah. Yes.
So what domain did you actually try this? What worries me is that if you actually see a large intra-class variance, you might end up either splitting existing known categories into two categories or not creating new categories.
Yes, so that is one of the limitations. We can split one of the existing ones into multiple if they nicely group into different clusters. But then, yeah, you can do some post-processing and merge the merge the clusters which look similar. That has been done in previous approaches, yeah. Any other questions? Okay. So, yeah, the point here was that we are not solving this problem completely, but we are giving a new kind of framework where you can do, you can learn existing classes as well as discover new. And that can be done even in better ways than what I am doing. So in terms of related work, I will just quickly go over it. So it is related to structural EM approach proposed by Neer Fedman in the way that we are also learning structure in the unlabeled data. And using this correspondence, we can say that our model also converges at local maxima for penalized log data likelihood. In terms of other work like which find correct number of clusters for k-means, these kind of algorithms are running it for different values of k, but we are doing a joint optimization. Then there is some work which does detect semantic drift in semi-supervised EM, and they are trying to model the negative categories as mixture model, and some of them are using the seeds of negative classes, whereas we are not doing it in cross-validation setting, so it's more efficient and we don't need any negative seed data. Yeah, there is some work in modified adsorption where they are introducing this dummy label which says none of the above. Our method is better because we have multiple dummy labels and it is inductive. Finally, there are some work in topic detection and tracking. The sole focus is on detecting new topic given all topics till point t-1, whereas our focus is on keeping the known ones purer, reducing the semantic drift. Okay, so now let us move on to experiment. Yeah.
Is this related to Jerusalem processes too? Because I think they address more or less the same problem. So when you have a new data point, either you assign it to one of the existing classes or you create a new class.
Yeah, that is a great question. So we have done some comparison with not Dirichlet process but with CRP. That is similar. It creates a new data point based on some prior knowledge of creating new class, and there are some experiments in the paper. I have some extra slides which I will present in the end if time remains. But what we saw was that they have some prior belief of probability of creating new class, whereas our method is using the posterior belief of creating new class, and those two can be combined and the method is even better. You can also have a prior belief and posterior belief. Okay, so in terms of data sets, we have tried it on the first data set is semi-structured data extracted from sports web pages, and this is made available by us. The second two data sets are like pretty common, 20 Newsgroup and Reuters. Note that they are completely labeled, but for our experiments we are simulating the setting that some classes are known and others are unanticipated. Okay, so what I am showing you here is how exploratory EM performs with respect to semi-supervised EM on macro average seed class F1, so that these methods are comparable. And for each of these data sets, we are randomly picking 5, 6 or 10 classes, generating multiple such trend test data and averaging the results over those data sets. Okay. So this is how semi-supervised EM performs when we use k-means, naive or von Mises-Fisher model, and this is how the exploratory EM performs. The bold face numbers are improvements, and asterisks tell you that it is statistically significant improvement. But these numbers are not making much sense unless I tell you how many classes they are created. So if they are creating too many classes, then of course the likelihood might be better. But you can see here that for some cases like k-means and min-max criteria, it's creating near ideal number of classes, detecting the number of classes correctly, and for von Mises-Fisher and Jensen-Shannon and the Reuters dataset, it is creating right number of clusters. So here the results show that these methods are not perfect, but they are trying to do something interesting, and whenever they are finding almost correct number of classes or clusters, the numbers are quite good. So these things are related to each other somehow. Now if you look at the same confusion matrices I showed you earlier, they will make more sense. So here what is happening is our method discovering these new classes, and thereby the semantic drift of seed classes is reduced. There are many other experiments in the paper which I don't have time to present, but like we changed the number of seed classes, number of seeds per class, and we compared it against CRP, and the conclusion was that doing this exploratory kind of learning is not hurting the performance of semi-supervised learning. It is improving only, and in some cases it is in most cases it is beating regular CRP or semi-supervised learning techniques. So the takeaway of these experiments are that dynamically introducing new classes can reduce semantic drift. So this is interesting. The near uniformity criteria we presented also gave effective results, and it was better than Gibbs sampling plus Chinese restaurant process in our experiments. And the last important point is that the purpose of this work is to stimulate this research where you can co-learn the new and existing things together. Are there any questions till this point? Yeah.
Can you go back to the result page? So you were evaluating on F1, and F1 is really sensitive on the number of classes, right? Like if you look at the last row, like the routers have like 65 different classes, and the best of F1 comes from predicting 62. And if you predict like 100 classes, you would get like really bad F1s, right? So here's like one trick during training. If you have a dev set and then you change your model selection to just judging by the F1, you know. Once you get the best F1, you stop, and then you pick at you know, how many classes do I end up with, say like 60 or 65, right? And then during test, you just say I stop at 65 or 60, you know, where I stopped at, you know, on my dev set. Would that give you like, you know, better?
Okay, so you are saying that we know about 10 classes, split it into 5 and 5 dev set, and do this training.
You split your data into train, dev, and test. So dev set would also contain samples of all 65 true classes.
Okay.
Right? And your model selection is just to find out how many classes would give you the best F1.
Yes.
Just to
yes, that can be one other approach. Yes.
Okay. So how about you know, you have like a 10 seed classes, right? What if your model selection violates this seed assignment on the labels?
Why is that?
You decided to split a class and then you retag everything and you find out the retagging violates your seed class.
Okay, yes, I should make that clear. So this might create lots of classes, but then since we know the labels, we are relabeling all the clusters, and it's like doing normalized mutual information kind of thing, because now there are more clusters than number of classes. So you label all the classes, all the clusters with labels, and then pick the majority one.
Pick the what?
Majority label.
Okay.
That is what is done in clustering. Generally, if there is no one-to-one correspondence.
Okay.
Is it clear?
Well, okay, what does your seed look like? Like for each document, you would know the category.
So that data point is seed data point.
Yeah. And then you retag that data point. What if you get a different class label?
So for the seeds, we are retaining them throughout the EM process. We don't change assignments of seed classes, seed layers, seed data points.
Okay.
They will always be in
Okay.
this. Yeah.
I'd like to comment on the dev train test idea. It seems to me that the whole point is that there's unanticipated classes in the test data. And the dev train test idea is assuming that in the dev class at least, you're covering all the possible classes, so you're violating the basic assumption.
Yes.
So you have to use dev to choose. She has like 6 choices for each data set. So you have to use dev or something to choose, because there's no single choice that works in all data sets. So there has to be some dev used to say, am I going to use min-max or JS or semi-supervised.
Yeah.
This is really interesting, and your talk was very clear, stimulating a lot of discussion. I'm just a little bit worried about
Yes.
the timing.
Yes.
So how about if we let you continue?
Sure. Yeah. So the next part is hierarchical SSL. There is less time left. Maybe I should hurry up. So in this case, I already showed you the toy example that we have the subset and mutual exclusion constraints, and the task is to learn classifiers for each of the categories in the ontology. The difference from what I showed you till now, the difference is that for now this particular cat data point, we are not assigning it to one of the classes, but we are assigning it a bit vector of labels such that there is one bit for each of the category. And for this particular example, we want everything animal and mammal bit set. What these, and note that this class ontology need not be a tree. So the NELL ontology that we have, any node can have multiple parents, and there can be overlapping classes, and our method takes care of it. So the first constraint is subset constraint. What it tells is the mammal bit is set, then animal bit should be set. The disjointness constraint says that one of these bits can be set at any point. So with this particular setting, the problem reduces to, for each unlabeled data point, we want this consistent bit vector assignment. Let us see how we do it. So we again use the same semi-supervised EM framework. The only difference is here when we are picking the classes. So here we have posterior distribution of class given data point, and the task is to assign a consistent bit vector that aligns with the ontological constraint. So for rest of the part, you can use any model of your choice, but for this particular part, we are proposing a mixed integer linear programming based solution which can incorporate the subset and disjointness constraint. So let us see how it works. For this ILP, the input is for each data point the posterior distribution of class given a data point, and the class constraints like subset and disjointness. The output is a consistent bit vector. What we are trying to optimize is the likelihood of assignment minus constraint violation penalty. So here is what the ILP looks like. You don't have to read it. Let me help you. So the first part is core of label assignment. The second part is subset constraint violation penalty. And the third part is penalizing for mutex constraint violation. If you solve this for each data point, you get the consistent bit vector. This might look expensive, but we have some approximations that you don't have to do it for all set of classes and constraints for each data point. And you can also do this in parallel. Now it's not order dependent. Okay. So for this there is some related work. I will quickly tell you the contributions. So contributions from previous work is that we are assuming only small amount of training data. We are not assuming a tree structure hierarchy. We are making use of training data, so it's not a clustering task. And so these ILPs are used previously by some approaches, but we are using it in a EM setting. So the labels produced are helping us learn better classifiers in next iteration. Okay, so this is how the method that I just showed you performs on NELL'S entity classification data. So we created these 4 data sets, also made available online, and the ontology for these data sets vary from 3 to 4 levels. What I am showing you is micro average seed class F1 for flat versus hierarchical approach. The flat approach is learning classifiers only for the leaf nodes of the ontology, not making use of constraints. And this one is constraint classification. You can see that it is improving over the flat, and the improvements are more as you go down the hierarchy, because this problem gets harder at the finer levels. So this was an encouraging result. Next question was, can we do better things with this rather than just entity classification? So we had a team in CMU working on information retrieval. They wanted to use our NELL knowledge base, but it doesn't have any glosses. So it cannot be used for many NLP tasks. And we started working on generating such glosses automatically. What I mean by glosses is natural language definition for named entities. For example, this is a gloss for potential gloss for Microsoft. Our input is a knowledge base which is gloss free. It has set of categories, ontological constraints, and entities belonging to these categories. And we also have some potential glosses. Say you take all DBpedia abstract, those are, or Wikipedia first paragraphs, those are candidate glosses. The output that we want is for each such gloss, we want to match it to the entity in NELL knowledge base or any knowledge base. So this is the task. It is challenging because the knowledge base is gloss free, so there is no training data. And that's why the name automatic gloss finding. So let's see how we do it. This is a toy example of an ontology. There are subset and mutual exclusion constraints. We know some entities that belong to these categories, like here strawberry, banana, fruit, apple. Note that here the entities are disambiguated. So if there are 2 apples, we know one is fruit and one is company. Our knowledge base also has lexical strings that belong to these, that can refer to these entities. And at this layer there is ambiguity. So here the apple with capital A can belong to either fruit apple or company apple. And that's why the problem becomes challenging. Now let's say we have 4 candidate glosses. Task is to assign them to correct entities in NELL. But we cannot do this because this looks like an entity linking task. The entity linking methods that are present right now, they assume that there are glosses on the knowledge base side, whereas we don't have any text. So instead, what we decided to do is we want to classify these glosses now. If we know that this apple in this gloss is referring to fruit, then we can definitely assign it to fruit apple in our knowledge base. But we even don't have these labels. There is no training data. So how do we do it? We apply a simple heuristic for training these classifiers, and this is acquired from word sense disambiguation work. If there are some unambiguous glosses like banana and Microsoft in this case, now you can label them with fruit and company labels. And now you have training data for categories in the ontology. If you can train on these training examples, then now you can predict labels for the ambiguous glosses, and this becomes a learning problem, semi-supervised learning problem. Further, you don't have just the leaf labels, you can also generate hierarchical labels, and this allows us to learn classifiers for each node in the knowledge base. Okay, so we do this. Now let me show you some toy example. So here all these black circles are glosses that we want to classify. The categories are vegetable, fruit, company and university. The ones that are already marked with some colors are seed examples, which are unambiguous glosses. So say this is gloss for banana and this is gloss for Microsoft. What we want to do is classify these ambiguous ones for apple a fruit and apple a company. To do this, we'll learn classifiers for each of these classes using the some seed examples. So it's semi-supervised learning. Further, we do it in hierarchical way such that the subset constraint between fruit and food is satisfied. The class boundaries are within each other, and the disjointness constraint keeps the class boundaries for food and organization distinct. If we do this, the hope is that the gloss for apple a fruit will come under fruit category and gloss for apple a company will come under company category. Now let's see whether that happens. So we applied it for our own NELL knowledge base, which doesn't have any glosses. It has 275 categories and we extracted 247 candidate glosses. We used 20K unambiguous glosses as training, and since we don't have any gold standard, we manually labeled around 400 ambiguous glosses with NELL entities. And let's see how our method performs. So the green one is GLOFIN, which is our proposed method, and we are comparing it against the SVM baseline and label propagation. So this one is a state-of-the-art semi-supervised graph-based learning method, and you can see that GLOFIN is giving slightly better precision, much better recall and much better F1. So because it is making use of hierarchy, it can generalize. So if some gloss, it is not sure whether it's a fruit or company, but it is sure that it's food and not organization, it can generate better labels. So that way it is increasing the recall when there are very few seed examples. Just to test the hypothesis, we used a gold standard free-based data which we got from Entity Recognition and Disambiguation Challenge 2014. We had 66 free-based categories and some 285 candidate glosses, and we had labeled ambiguous glosses for testing, 50K. And on this dataset, we got similar results. So it's not NELL specific. It gives little better precision, much better recall, and much better F1. So this is how GLOFIN works, but that's not all. So once you generate the glosses for a knowledge base, now it can be used for standard entity linking tasks. Further, it gave us links from NELL knowledge base to Wikipedia and through Wikipedia to Freebase. So now you can link your knowledge bases. You can also replace the Wikipedia glosses by any online glossary, and now your entities in your knowledge base can have multiple definitions. This is also hinting us towards exploratory learning, because I'm categorizing a gloss as fruit or company. If it is categorized as fruit and that particular fruit is not present in the knowledge base, I can add it. So it has exploratory aspect. I like this work because it gave rise to 2 other projects in my group, and I'm actively involved in these. The first one is large-scale definition extraction. Instead of limiting ourselves to Wikipedia, we are going to the entire parse of ClueWeb, which is a big corpus of 500 million pages. We are classifying the sentences as definitional or not. For this, we can get large training data, and this is a supervised classification. Once we do this, now we can link NELL entities to many occurrences of entities in these sentences. Further, another interesting aspect is using this in word sense disambiguation. So now you can replace our NELL knowledge base with WordNet hierarchy. We didn't make any tree structure assumptions, so it can be used for WordNet. And you can replace the unambiguous glosses by unambiguous word occurrences. And we are working on this with a University of Haifa professor and learning these word senses. I showed you these two pieces of work, but there is also an other project that I am working on, which is hierarchical exploratory learning. I will just show you the glimpse of what it is trying to do. So here we have an ontology as input, but it is incomplete. So what our method is trying to do is it can dynamically add nodes to levels in this hierarchy, so that at a time you can learn the existing categories and discover these new in hierarchical way. And what this leads to is, like, this is the same diagram I showed you in the first slide, which is traditional knowledge extraction. Our methods are improving this knowledge extraction in the sense that along with new facts, now we are proposing new classes that can be added to the ontology. And if you are pessimistic about adding them directly to the ontology because they might be split, a user can sit in between and pick the meaningful ones. And this process is much more simpler than thinking in the air and coming up with classes and examples. So what this enables is something in between closed domain ontology driven knowledge extraction and open domain knowledge extraction. This is something in between. Okay. Further, it's not limited to knowledge graphs. We can do this in any classification or clustering setting. For example, email categorization or news summarization. And I'm excited about this piece of work. Some other research projects I've worked on. I have 1 minute. Okay, so I have also worked on an information extraction from semi-structured data, and we also learned some unified representation of entities, which is published in STM. I have also worked on information retrieval. This is my master's project, keyword search on external memory data graphs, and recent ERD challenge. And if you are interested in talking about any of these are some other miscellaneous projects. We can talk in our individual meetings. Finally, I would like to thank my thesis committee, my master's advisor, and all the wonderful collaborators who helped me do this research, and thank you.